So, good afternoon to everyone. Welcome to my session. I will speak about optimistic concurrency and your blocking problems. So my name is Margarita Naumova, or my friend call me Magi. It's easier, I think. So I'm working with SQL Server for, well, a lot of time. I'm a trainer, consultant, and I'm happy to come back to Sweden every time. I really like this country, so sometimes I envy you that you live here. I worked for Microsoft for 5 years. I was part of the worldwide technical leadership team, but at some point I decided that I want to leave the company, and now I'm working on my education program called SQL Master Academy. I'm doing a consulting job. A couple of years ago, I decided to upgrade all those certifications to only one, which is my precious. It's a Microsoft Certified Master, and as Brent also told you yesterday, it means that I really like to talk a lot. Let's approach the blocking problems today. Does the optimistic concurrency resolve all your blocking problem? Well, if you are sitting here, and that means that you believe that it doesn't resolve all your blocking problems. So I'm telling you, it does not, for sure. So it resolves some of them, of course, but not all of them. There is some specific usage of optimistic concurrency, and the goal of my session today is to explain you and show some examples of the proper usage of optimistic concurrency, and some examples of where the optimistic concurrency is not your option, and what to do if you still have blocking problems and the optimistic concurrency doesn't help. There is one sentence here that I probably have to put in at this moment of my session. Yesterday I learned, surprisingly, that Microsoft doesn't call the snapshot isolation levels an optimistic concurrency. They call the new hackathon model of concurrency an optimistic one, optimistic in-memory concurrency isolation. Wow. And they called the snapshot isolation something else, I don't know. But anyway, I will talk about well-known optimistic concurrency as we all know about it. As optimistic concurrency. So if optimistic concurrency doesn't resolve all your blocking problem, then we reach the point when we have to describe what is the difference between blocking cases. So the first approach when we investigate blocking is just to find out what is the root cause of blocking, why you're blocked. And there are different kinds of blockings based on the different reasons that blocked each session. So our first goal today, and hopefully in your daily work when you approach blocking, will be to find out the root cause of blocking case, why you're blocking. So in order to do that, I will start with some, that's my hardware problems that I usually face. Okay, so first of all, I will simulate absolutely simple blocking situation in order to show you where you can find the blocking information and how can you describe and find out what is the root cause of the blocking. So I'm going to use an AdventureWork database because it's kind of familiar for you, I think. And I'm going to use a salesperson table, which is a relatively small table. It has only 17 rows. And I'm going to play with territory ID, which has 3 rows of territory ID 1. And at the first time, I want to update the bonus field of the salesperson for territory 1 in order to stimulate them to sales more. So I'm starting a transaction, and at the same time, I'm starting another one, which is trying to read those rows. So how I'm going to check what's going on, actually? So first of all, when a user complains, we usually we start with a waiting task because we are waiting for something. So waiting task is your first DMV that you can check when you explore the waiting problems. And you can easily find that you have a wait type of waiting for lock, waiting to obtain a shared lock to a currently modified resource. And I can see that the blocking session ID is 52, and some resource description, which is kind of complex to find out what is the problem. So your second ultimate DMV that stores all the information about obtaining locks and for the whole SQL Server instance is sysdm-tran lock. So whatever fancy tool you use for blocking, for exploring blocking, every tool actually uses this DMV because this is the only DMV that stores every step in obtaining locks inside the SQL Server. So I obviously have a lot of information in this DMV, so I will select only specific columns that are kind of interested in this for you in this session. So I have a resource type, I have a resource database ID, and I have some resource description, which is also kind of not describing me actually what's going on and what is the resource is. So it's definitely, I can say that I have a select lock, which is a reader, that is trying to obtain its select lock to a resource that is holding an exclusive lock. So what is the resource type here? So I have a key level lock that is obtained on an object, and the resource associated entity ID is the actual value that gives me an information, that could give me an information about the object. So I have a specific resource entity ID here, and I can query the syspartitions in order to obtain the object name. And yeah, I have to be in the resource database, by the way. So I can see that I have a salesperson table which has blocking. So if I write a little bit more, then I can see a lot of information about the object and about the locking mode, and it's kind of a more fancy and more readable. It's just joined between the dm-tran lock, syspartitions, sysindexes, etc. So if I want to see the statement, that is what is executing against the table, and by the session ID, for example, then I can just query additional information by querying the function sysdm-exec SQL text. This is a very long select statement. I don't believe that you want to write this on your own. And I strongly recommend you the Atom Mechanics store procedure. Has anybody used this? Great. So
The atom mechanics stored procedure, who is active, tells you a lot more information about the blocking scenarios. And here you can find really a detailed information about which session what is doing and how long the lock takes against the table. So there is a specific information about the sessions that you can gain from this. And you have a blocking session ID and the root blocking session, and their status. If the status is sleeping, then the session is doing nothing, just probably something goes wrong, or you have to blame your developers. So this is for sure, but the session could do something else. For example, could be in the suspended state because of waiting for a resource, which I called a resource blocking. And the resource blocking means that you probably have a resource problem and you have to investigate what is the problem. You could have a problem with the memory, with the CPU, or waiting for the disk, and this session could be in a different state. This tells you a lot because it's a root cause of your problem. So beside that, you have an additional information, and you have an isolation level for your blocking session, and you could see what's going on relatively easily. So this is the case. So when we have a blocking, when it is considered to be a problem, well, we have a blocking because we have incompatible locks between between two sessions. We can have blocking because of long duration that the session that is holding the incompatible lock takes. So the duration is something that is really important, because if this takes a lot, the users just complain a lot. So we can have readers that are blocking each other, and we can also have, oops, sorry, that's not my transaction here, so I will just roll back transaction, and, oh my God, sorry about that. Okay, so let's finish this transaction. So there could be another case of isolation level that is, for example, repeatable read, or that a select statement takes a shared lock for a long time. It's a case when your queries are very complex and they really take a lot to complete. In this case, if you want to update the table or the same resource, your writers are blocked. This is the case when you want to increase the isolation level because you want the same select to return the same result inside a transaction. In this case, you just increase the isolation level in repeatable read. And in this case, also, your writers are blocked even more, or even for a long time. You can obtain this information from the atom mechanics store procedure, and you can see the isolation level of the session that is blocking others. There is another specific case that I faced with my customer, and it's a very interesting one. It's connected with a serializable isolation level. So I'm not expecting that you use a serializable isolation level on your every solution, because it's really an exception. But it could be something that you even don't know your application is using. So the case with my customer was that I realized that they are using the snapshot isolation level, the serializable isolation level, because they were using an old version of the entity framework.
and they leave those settings by default. And when entity framework generates a lot of strange-looking code against the SQL database, it just switched to the serializable isolation level. And inside the serializable isolation level, you have this strange behavior, which is not so strange, by the way, but anyway. So I have a transaction history table, and I'm switching to the transaction isolation level serializable. So I'm starting a transaction, and I'm holding the select lock during the whole transaction because I'm in this isolation level. So it's clear that I am holding this, but just, okay. And by the way, I'm not just holding a select lock or shared lock on my resource. It's even worse. I have a lock escalation here. So shared and exclusive lock are locks that are usually on the page and or on the key level. If you have exclusive lock or shared lock on the object level, then it means that SQL Server escalates your lock to the object level. In such a way, it reduces greatly a concurrency in your database. So it's a kind of normal if I select so many rows to have a lock escalation. But if I have, do you know what is the threshold? 5,000 rows. So if I again start a new transaction and I select, I select less rows, for example, 2,000 rows, then I shouldn't have a lock escalation, but I still have a lock escalation. And this is because I don't have an index. I don't have an index on the reference order ID. And the SQL Server just uses in the execution plan the index scan, clustered index scan, and because it cannot obtain a zone or range lock, it just locks all the table. And the lock becomes escalated because it cannot produce the execution plan and accessing the table in different way. So if I just, escalating lock prevents me of even inserting rows that are not part of the row range. In this case, if I just create a non-cluster index on the reference order ID, then I can start a transaction again. Did I execute? Okay. So, and if I execute this transaction again, then SQL Server can easily lock a range of reference order ID, and in this case, it just perform a key range lock. I can insert in the table without any problems a record which is outside of this range. So indexes are actually something that could help you in those situations of blocking. So there are different reasons of blocking. I try to summarize them as writer block readers, as resource blocking, when the transaction performance suffers, and that's why the others just wait for the first transaction to complete. Definitely, lock escalation is something that you can blame for reducing concurrency in your database. Exclusive lock, you probably know that when you begin a transaction and you start an update, then exclusive lock is held by the end of transaction. So if you start an update early in your transaction, you will have a longer exclusive lock. Increasing isolation level or obtaining a shared lock it could reduce your updates also. If you try to alter the table while you're performing something inside, it is also a blocking case. So schema blocking is a classic one. So that's why it's important to not do that in production environments, of course. So there is a case of writing block writers, block writers, when your exclusive lock are incompatible, of course. So you couldn't obtain an exclusive lock of the table from different sessions. So there are different ways to deal with blocking. I found really creative ways of doing that while I'm doing a performance tuning and troubleshooting project. So the people do really different scenarios. Some of them is just controlling a lock escalation on the table level or using the trace lock, which is very dangerous, by the way, because you affect the whole SQL Server instance, and your memory could become a problem as a resource problem also. There is a set lock timeout, which is also something that I wouldn't recommend at all, because setting lock timeout is something that you can do on a session level, but when the timeout, when the session reaches this timeout value, it's just cancel your statement and it continues with the next one, even if you are inside a transaction. So it brings the error 1222, and if you have not an error handling of this error, you will be in a deep problems. So the other case is using a non-lock or read past hint, which is a way to completely give up from a data consistency. So sometimes probably it's better go to the file system instead of using the SQL Server, because the main case of the database is to prevent the data and their consistency. So no lock is actually setting transaction isolation level to read uncommitted, which is reading a dirty data while they are updated currently. So you never know how the transaction completes. That's why none of them is a good solution. There are other solutions that includes creating indexes, as I showed you. The general rule here, if you can isolate your transaction in a covered index, or your update statement, or your select statement in a covered index, then you could achieve separation of your session and their locks, and you can avoid the blocking in such cases. Partitioning is a classical scenario of that, and but it's not appropriate for every scenario to create just partition. So if you have specific writers blocking, then you could just check for iterative logic for using cursors, for example, which is a favorite one for some developers. And long-running transactions are also important. Of course, those are really general instructions, but they are working for most of the cases. So beside that, they usually take a lot to implement. So there are two more options. First is the optimistic concurrency model, and the second one, which I hopefully can show you, is in-memory OLTP in SQL Server 14. So I'm not going to explain in details the hackathon thing, but I will try to show you an example of reducing greatly the concurrency and really increasing the throughput. So optimistic concurrency is based on row versioning, comparing to the pessimistic concurrency, which is based entirely on locks to protect the transaction logic and to isolate transaction from each other. So when a row is updated, then a SQL Server just create a pointer to the older committed version of that row, which is saved, guess where? Inside a TempDB. And the older row is saved inside a TempDB, and your modifications occur inside your original database. So every modification actually transfers your older row inside the TempDB, so your select statement will not hold lock in your real database, and your select statement will not wait, but will read the previous committed version of your data. So in order to save the pointer, the SQL Server adds additional 14 bytes to every row. And this is something that you should consider as increasing the table size. You definitely need a version store size. We definitely need a TempDB. So this is another big consumer of your TempDB. So you should be very careful about setting the TempDB and placing the TempDB in a fast drive. And increasing the TempDB enough. So versioning is something that is self-managing. There is a process that goes through the TempDB and just removes the versions that nobody will take care of. And this is something that you don't have so much management efforts to, but you have to configure your TempDB in order to be fast and to be big enough. So in this case of optimistic concurrency, of switching to optimistic concurrency, you have readers that are not blocking writers, and writers that don't block readers. So this is the ultimate case when you can use your optimistic concurrency models. But you still have locks, and you still have blocking. And you still have writers which block writers, because your updates, your data modification still holds lock in your original database. So you have still exclusive lock. You can have lock escalations based on the exclusive lock. And beside that, as a benefit, you can have a conflict between writers and writer. So implementation is based on the two models. First is a read committed snapshot isolation model, which works at the statement level versioning. We call it statement level versioning because it works exactly the same as your read committed isolation level in pessimistic concurrency. But instead of waiting for the update to complete, the select statement just goes to the versioning store and reads the previous version of your data. So the read committed snapshot isolation level is implemented as an alter database statement or as a database option. You don't need any modification to your application or to your database. The other one is a snapshot isolation level, which is an analogy of repeatable read in pessimistic concurrency, and you have a select snapshot isolation level transaction in which you read every time you perform a select, you read the same data, so you use a transaction store, a version store in your TempDB. So in snapshot isolation level, you can have conflicts, and some DDL statements are not allowed within the snapshot isolation level transaction. You cannot perform some alter statement. Beside that, if you have a snapshot isolation transaction, you are just, you can have the following problem. If your concurrent session just modifies the table, which is allowed, so you probably select the table, you do nothing else. So your transaction has a problem and control back in this case. So there are situations here, especially in snapshot isolation levels, that are very specific and could potentially lead to problems. So the select statement, my delayed animation. So the select statement in a snapshot isolation level just reads a version store during the whole transaction, the whole transaction, not just the statements. Okay, so let's try to see. Okay. I'm going to show you a short demo of optimistic concurrency and especially some specific cases of conflicts and the case of DDL problem. I'm using the same data and the same database again, aligning the state, the value of the table, and switching to read committed snapshot. So as I told you, I have a read committed snapshot altering at the table level, at the database level. So there is an issue when you want to switch the read committed snapshot isolation level. Strangely enough, it requires to be the only connection to your database. So you have to exit the database, or you can just use the no wait or rollback immediate. You can check if this is switched on, is read committed snapshot isolation on. Okay, so let's see if I can really have locks in this isolation level and what is the problem that I can resolve with this switching and what problem remains in this case. Okay, so let's just copy this statement. Okay. And start. So I'm starting a transaction which is the same as I did before. In this case, I'm starting a concurrent transaction, and I'm just reading the previous version of the data, so I'm not waiting here. But what are the locks that exist in this case? I still have locks, and I still have an exclusive lock. But the change here is actually the behavior of select statement. So the behavior of select lock. So your select statement or your shared locks are gone. So you don't have shared locks in your production database. This is this actually addressed the main problem of readers and writers, and that's it. So if I just commit this transaction, okay, so because I'm at the statement level optimistic concurrency, so if I have a bonus of 4,000, if I read this again inside the same transaction, then I will see the next version of the data, the next committed version of the data. Okay. Oops. Okay. What about the next level? What about the snapshot isolation level? So here, inside the snapshot isolation level, I'm going to show you directly a conflict. Actually, if you try to write, to perform both updates on your data, then you will still wait. But let's save a little bit of time. Okay. So first of all, I have to switch to the snapshot isolation level. This switch is something that is performed very fast, but it's on the is performed on stages. So in order to be sure that the database is switched to the snapshot isolation, I have to check the state if this is on, because you can have it in transition state. While the transactions which are currently running in the database are switched to the snapshot isolation, which does not mean that your every transaction is switched to a snapshot isolation level transaction, but just to prepare for the snapshot isolation level. Okay, so first is to start a transaction that is so what is the value here? It's 3,000, and I'm beginning a transaction here. So in another session, I'm starting a transaction isolation level snapshot. Okay. And the problem here, and the difference actually, is that I'm reading the committed version of the data, and if I just if I just complete the transaction, then I will not have this data anymore. So I will read the same data inside the select statement. No matter how many select statements I did in my snapshot isolation transaction, I will always read the same data again and again. So even if I have an intermediate state of the data, then I'm still protected with the snapshot isolation level. Okay, so how is the update conflict? What I can do with an update conflict? So let's clear everything here because I'm kind of confusing. Oops. There are a lot of sessions and a lot of transactions opened right now. Okay, so let's close this one also. And let's see what is okay. So another transaction. Okay. So what is the point? I'm still having a 3,000, okay? So if I just start another update inside my snapshot isolation transaction, which is a concurrent update of this one, then I'm having a conflict. And a conflict says that a snapshot transaction isolation is aborted, meaning if you accept this, while you have both a couple of updates, then you have to have a retry logic in your code in order to try again the transaction logic. So that's the point in a snapshot isolation level. If you implement read committed snapshot isolation, then you don't have any conflicts.
But you are not allowed to use a different isolation levels also. So you have to be very careful when you work with a DDL statement in a snapshot isolation level. So DDL statements are very dangerous because they could potentially roll back your transaction even if they are not executed inside a snapshot transaction. So how to choose between optimistic concurrency model then? So read-committed snapshot isolation, or RCSI, is a concurrency model that gives you more benefits, actually, with a less cost because it needs less cost, less space in the TempDB. It saves just a statement level version. So it saves version as long as they are needed for the running statement, for the currently running statement, not the currently running transaction. So RCSI supports distributed transactions, but CI doesn't. In RCSI, you cannot have update conflicts. But I had a case when, with this same customer that I told you about, when we switched off the snapshot isolation level, the serializable isolation level, and we perform a monitoring against the weights of the database. So we realized that there are a lot of lockings behavior. So we tried to set up the database in RCSI. After that, their logic of getting the data for getting the transaction ID for some insurance policies just broke because they end up with a duplicate numbers of the insurance policies. And just because they didn't realize that they just read the whole version of the data and somebody else just read the same version of the data and they just can update in the first wins. So the second one could potentially be the problem and be also, because this is not a primary key actually in their case, so they can end up with updating or inserting the same value of the insurance policy. So in this case, we decided to try just to leave the RCSI model because it really resolved a lot of problems of concurrency. But we decided to create a model for obtaining the insurance policy IDs as a different logic outside the database, as a service. And this worked perfectly. We guarantee that there are no repeatable numbers in this case. So in general, RCSI does not require any changes in your default in your database or in your stored procedures. But anyway, my advice is always test this. So repeatable read consistency inside a transaction is not supported in the read-committed snapshot isolation, and that's why those problems that I talked about exist. So you could perform a CI, so you could switch to CI, but you have to be careful about rollbacks. So the optimistic concurrency resolves just specific problems of blockings. First problem is it resolves completely writers and readers blockings, including escalation of shared lock, including lock duration if the concurrent transaction is a reader, and including the holding an exclusive lock for a longer time than it should. Then your transaction should do that. And lock escalation of insert in a serializable level, actually because you don't have a serializable level. So what problems optimistic concurrency doesn't resolve, and how to perform how to find a resolution in those cases?
First of all, optimistic concurrency doesn't resolve your resource blocking. So if you have a resource blocking, then you have to find out or to perform some investigation. What is the resource problems? Is it a lack of index, or is it a disk performance problem, or is it a memory misconfiguration of your server, or is it something else? So this is the first task to do in order to resolve this problem and to see if the locking persists, if the blocking persists. And in this case, you will have to either resolve the problem or see the real reason of this problem at all. So schema blocking is something that also is not resolved by optimistic concurrency, because you have a versioning of rows, but you don't have a versioning of the metadata. So that's why you have to perform something additional in order to have this, to avoid this schema blocking. In 2014, we have an online index rebuild locking priority. So we can define a locking priority if this comes from the maintenance task, or if this comes from a partition switching. So I have this blog post of online index rebuild, which is really an interesting case, but I couldn't tell you much in this session. So there are a couple of problems that still persist after you switch to optimistic concurrency. And those problems are connected to writers or to concurrent updates. So if you still want or still have concurrent updates which that block each other, then you have either to accept blocking or return to the pessimistic concurrency, or you have to accept eventual conflicts and roll back the transactions. Or you have to have a retry logic in your code for those cases. If you have lock escalation, then probably there's some indexing case, so index troubleshooting, or some design changes. So there is a special blocking case that is called a latch contention. Latch contention is something that is very common for very high concurrent and with a lot of transaction OLTP workloads. So what is a latch? In shortly, a latch is a lightweight lock, but it's just a statement, actually, a lightweight lock. It's a latch is a locking, kind of a locking, but it's internal for SQL Server in order to preserve the physical consistency of the page. So you don't want to just broke the page, physical consistency of the page, while you writing it to disk, or while we're reading it from the buffer pool. So that's why SQL Server puts those latches for 1 or 2 milliseconds maximum in a duration, and it protects in such a way the physical the physical page inside the buffer pool. So you obtain or you see a latch contention in very high concurrent workloads. For example, if you have a situation of SQL of increasing clustered index key, for example, with identity property. So in this case, imagine that you have a lot of transactions that are trying to insert a record, and all the transactions are trying to insert a record in the last page of the index. So in this case, a latch contention occurs, and your throughput is generally decreased. So there are different kind of solutions for these problems. First solution is just use a non-sequential index. Well, it creates a lot of additional problems, actually, with fragmentation, with page splits, etc. So it's a solution that definitely should be tested, and there are specific settings that you have to perform in order to implement this. So probably you will need a very fast transaction log, and you will need to put the fill factor in order to leave a space inside the index. So the next one is just to partition or to distribute those sessions between several partitions or between several bit trees. So I'm offering you another view of this solution, and I will show you how much it takes to so we have 10 more minutes. Okay, that's perfect. So I'm going to show you how it's performed, how it's done in SQL Server 14, and how you can resolve almost all your blocking problems with SQL Server 14. Well, that sounds promising, and yeah, it's really work actually. So I will use a virtual machine that is from the Microsoft people, Microsoft guys. They prepared this virtual machine, and I'm using it because I'm trying to prepare content for a Microsoft conference. So it's kind of a benefit for me here. So I will use this virtual machine also. Here we go. Along with an application that simulates a high-intensity workload against the ticket issuing database. And it gets transaction per second, and it gets the level of CPU usage and the latches per second. So this is a regular database which has one table, and I'm not going to go through the store procedure that performs this workload, but in general, there are a lot of inserts as a ticket reservation, and there is a procedure that reads those tickets. So it's a kind of scenario of very high concurrency with reading and writings. So if I start this, you see the level of throughput that I can gain in this situation. By the way, you have to hear my laptop complaining here right now because of this CPU increasing. So this is the level of the transactions that I have currently. Transactions per second is about average of 6 to 700. So what do I have as a locking here? So I have a lot of locks, by the way. I have locks that are waiting, and those locks are shared locks. So if I check those complex statements with a lot of joins, then I can see that I have shared exclusive lock granted on a key level of the ticket reservation table. Those are short transactions that are sent to the database. Beside that, I want to see, and I will show you, the waiting tasks during this simulation. And you can see that I have a lot of page latch. And beside that, I have locking also. So if I start, okay, let's stop this. I really have to have a laptop by the end of this session. So if I just switch the database concurrency module to optimistic concurrency, as it seems that it will resolve my problem because I have those shared and exclusive lock that fight each other. So if I do that,
So in this, yeah, I'm using rollback immediate, so it definitely works. I don't care about the transaction right now. So if I start this again, wow. So I don't gain so much benefit. Actually, I even lowered my throughput. And that's because my TempDB is just very slow. And I just don't do so much with this optimistic concurrency. What is the page latching? What are the weights right now? So I have a lot of page latches, and they have a duration. Oops, sorry. I don't have a zoom here in the virtual machine, so I was trying to zoom in. So I have a lot of latches, and some of them, if I just check again and again, you'll see that those latches are taking more time and more time. Actually, there is a kind of a threshold. If a page latch takes more than 2 milliseconds, then there is an issue with the page latch contention. You can just get a snapshot before your workload, and you can gain a snapshot, a delta after that, and you can compare the average time of page latch weights. So in this case, I really have a large contention, and I can check the resource in this way. So just to have the object, I will stop this. It's not an optimization. I can see what kind of resource is that using the partially documented DMV, which is the DMDB database page allocations, which is kind of a replacing of DBCC int or DBCC page in a combination. So if I check this, then I will see that I have a page latch on tickets reservation detail, and this is a specific page of type index page. So this is not an allocation page, this is not a page free PFS page, it's just an index page. So it's part of the battery structure, and all of my sessions are going to this page, and they just get there and they block each other on the page latch. Okay, so in order to find out if this page latch creates problems, I will just drop this database and create it again. And it's not necessary, of course, to drop your database and create it again because of Hackathon. But it's just how this works in my virtual machines. So it's still in CTP2. There are some statements that will be changed probably in the release, but I want to start from a clear database and to show you how the upgrading or changing the model of the table to the Hackathon can resolve those problems, and how much the benefit can I achieve. So I'm not going to dive into the Hackathon table, but just to mention the things in this script. So first of all, I will switch to the Hackathon database with creating an additional file group and a file stream file for the checkpoints. And I will switch to, I will create a new table, which is a Hackathon table. Probably you know that you cannot perform an alter table. So you can, for example, rename your disk-based table and just create a Hackathon table. So in Hackathon table, I am creating a memory optimized table. Have you been to the Kellen's Delaney yesterday session? How many of you? Oh, great. So, so this is my in-memory table.
You know already that we don't have data pages. It's saved in memory, so it's something that is very optimized for those workloads. Okay, so in this case, I'll just switch to. I will start again this thing. Okay, so let's take a baseline in order to compare this. Just for. Okay, so this is the baseline without hackathon tables, without optimistic concurrency. And now I'm migrating the tables, the only table that I have problem with. And because this application is written with hard-coded values, then I have to just execute this manually. And this does not change anything for my code. So I'm using the combination of standard store procedures with in-memory table. I'm just changing the table from disk-based to in-memory table. And I'm starting. Wow. So it's 6 times faster just with this one, just with this change. Let's see. So according to this picture, I don't have any page latches. Okay, so let's check this. I really don't have those page latches. So I don't have waiting locks either. So no locks, no page latches, and this is because the in-memory table and in-memory in Hackathon works with the multi-versioning concurrency in-memory optimistic control. I'm not sure I tell you the right sentence, but anyway. So I will stop this and I will try the last one, which is migrating the stored procedures. Or this means that I'm migrating the procedures to the native compile, to the natively compiled stored procedures, which are a compilation of code and storing this as a DLL and calling the DLL. This greatly reduces the CPU contention and the CPU usage. So in this case, I'm starting this again for the last time. And I gain about 10 times more throughput. And about 20, I think, times, or 15 times more than the initial one with the disk-based tables, without latching, and with not so much effort. Well, it doesn't mean that I will change everything here to be an in-memory structure in order to just resolve my blocking problems, but this is really an option. So, what did we cover today? So, as a summary, first of all, when you have a blocking, we have to consider researching this blocking using the specific DMVs or other mechanics stored procedure. The primary goal is to find out why we are blocked and what is the common reason, the root cause of blocking. When we find out the root cause of blocking, it's easier to get the right solution to the blocking problems. So if we choose an optimistic concurrency in case we have readers and writers that are blocking each other, then we have to take care about our TMDB and we have to perform a careful testing of our statement level or snapshot isolation level transactions. So if you have a page latching problem, along with the locking problem, then you could probably consider some other solutions, like partitioning, or like, for example, using non-sequential leading key of of an index. But anyway, you could really test. I encourage you to read the white paper of Kell and Delaney, hackathon white paper. It's published, so it definitely says a lot about hackathon, and you could just consider this as a potential migration in order to resolve your blocking problems, because this is one of the main benefits of SQL Server 2014. Okay, thank you for your attention, and enjoy the last of the conference. Thank you.